Is on.
There we go. Are you hearing any background noise, by the way, from my audio?
Not from here.
Nope. Okay, good. I do have some ambient music on, so I just want to make sure that that's not interfering with anyone. All right, so maybe give it another minute or so. 7:34. I see a few are still streaming in. That's Kevin. Hey, good evening. All right. Wayne, just so you know, Peter forwarded me the presentation just in case there's any technical glitches, so I'm all ready to go with that. Okay. I have 26 slides, if that sounds about right. Although slide number 20 says discard, so.
Yeah, that's the end of the current deck.
Got it.
I'm growing it very slowly, so I thought what I would do is a portion of it today. I'll run until basically I've used up enough, I think, time with the meeting, I guess.
Okay, so we've got 10 of us here by the looks of the counter on my screen. I guess I got to stop moving my pointer around because it captures that on the video. So we might as well get the show started. So good evening. Welcome to the December 7th, 2022 AF Mixer for the Homebrew Group. So yes, as mentioned, Peter is ill. He would otherwise have been hosting this evening. So I'm, for better or for worse, subbing in for him this evening. So tonight, looks like we have a new guest with us, Charlie, correct?
Yeah, that's right. I'm part of the Kingston Club, and Peter's invited me to drop in. The topic looks interesting, so I dove in.
Okay, that's great. No, glad to have you here. So VE3XCC, I see. So welcome to our meeting this evening. So
thank you.
You out of Kingston?
Yep.
Yes.
Yeah. Okay.
Are you part of the Carricks as well?
Yes, I am.
Yep. Okay. Good. All right. So we have one presentation that we already alluded to. Wayne, VA3 NWH. Is that correct? That doesn't look right, but that I guess is correct. Lowercase is what's throwing me off, maybe. He has a presentation for us this evening, Intro to Q Measurement and the Ring Down Method. And we may be getting the full presentation, maybe not. You had mentioned in an email that you've got a bit on Wes Hayward's as a possible, I guess, continuation of your talk. So I'll let you discuss that, I guess, when it comes. But anyone else have anything that they would like to, put on the agenda for this evening, just so we don't miss it and I can cue it up?
No.
Nope. All good. Okay. All right. So I think we will just jump into it right now. We will be doing a round the workbench afterwards to just have everybody check in, see what is on your workbenches. Charlie, it's very informal, just so you know. This is our mixer meeting, meant to be sort of around the water cooler kind of event. These third Wednesday of every month we have more formal presentations usually, but really most, the meetings are kind of similar, to be totally honest with you. So, all right. So Wayne, if you are ready to proceed. We can go ahead.
Very good. Just let me do the business of getting my screen shared first.
Okay.
All right, share. Entire screen, share that.
Just a reminder, if anyone has any dogs barking or unruly inhabitants of their house, if you could keep your mics muted, that would be appreciated. So far, so good, Wayne, with your screen.
Thanks. Okay, so the reason of my not being sure how far I'll get on this thing is I actually don't know how slow I'll be talking through it. So I thought if there's nobody else talking but me, I'll watch the clock and say pull the plug at around 20 after to give us some time for the sharing. And if you need me to quit anytime sooner, let me know, Eric.
Okay.
Okay, so today we're talking about measurement of the Q factor, and I'm going to share the story in segments. The reason I got into this is I was having a series of failures of amplifiers I was trying to build that were all related to tune amplifiers. So I had variable tune amplifiers, non-variable tune amplifiers, but I just wasn't getting it right. Now, amplifier design is, say, tricky for beginners. So it could have been anything. It could be caused by my inability to figure out how to match normal impedances and stuff like that. But I took it to heart that I really didn't understand how the resonant circuits worked in terms of how they appeared to the circuit and how you would make sure that you didn't tune or detune them. And as a side effect of that, I realized I didn't have any way or any knowledge about how you would measure Q itself. Like, how's that done? I've heard of Q meters and I've seen them once or twice at ham flea markets, but never sort of bought one or tried it. So what we're going to do is we're going to start with something which I don't believe to be a contender for your lab as a serious measurement technique, but it's so freaking cool I just had to share it. It was the first thing I found, and I was wondering what this was because when I was looking at Q methods, it's called the ring down method. I have actually 5 approaches here. None of them include make your own Q meter, by the way. I don't think that's really a feasible option. And I will explain that, I think, at some time in this series. There's probably a 6th section when I actually figure out how to write up all of the measurements I've taken about the various caps and toroids. I spent a couple of weeks after I prepared this deck using the tools that I built to do a lot of measurements of the capacitors I have in my shack and my bins parts and a bunch of toroids I want. Okay, so let's start with the ring down method. So my search on the internet came up with this first, and it's just an interesting thing, I think, is because most of the time when you're measuring stuff, at least in my experience, you're dealing with the frequency domain. You're dealing with the magnitude of a signal as it varies through a spectrum, okay? So this one here is a time domain thing, and it works on an oscilloscope. And it works on the principle that if you'd have a resonant circuit, if it were pure and didn't have any resistive components to it, you could hit it with a signal. You could basically wrap it like you would a bell or a tuning fork, and it would ring forever. And the ringing would be essentially a sine wave that goes straight across. But because there is some physical resistance sitting in the circuit, of the tuned circuit, and in the coupling to the measurement apparatus that you've got surrounding it, the resistance causes that oscillation to dampen over time. And if you do the math, which I won't show you, but it's right here on the screen here, there's a mathematical formula that you can derive that says, if I simply count the number of cycles until I get from any measurement to half of that measurement on your oscilloscope, then multiply that number of cycles, full cycles, by the way, up and down, by 4.53, you'll get the Q. of the circuit you're measuring. Which, when I heard that and I saw that, I had to try it. So this is about my first attempt to actually do a Q measurement as well. So basically, you have to find a way of providing an impulse to a tuned circuit, and you have to find a way to read it off without loading it down too greatly. So we'll talk about that in this slide. I'm getting my information from a wonderful site on the bottom here. Eventually, I'll stop on a slide where I have the all these things listed. So if you want to take any notes off of them, feel free. The gentleman whose name is Jack has allowed me to use his graphic because it would be hell for me to try to draw this myself. So this is, we'll call it a typical setup for a measurement. You have your oscilloscope with your 10-to-1 probe, and it's connected to a parallel tuned circuit. So there's an inductor and a capacitor. And this is the first thing they'll say about measuring Q. It's fundamentally about resonance circuits. There are people that will measure the Q of an inductor and a Q of a capacitor, and I've done that. But it's done usually in the relationship of using a tuned circuit first, and you make some assumptions about the value of one of the two sides, as we'll see. The nano VNA potentially has the ability to measure an inductor by itself, but I think that's kind of problematic, and I will get to that eventually. So on the other side of your tuned circuit, which contains an inductor and capacitor, you have a some way of getting energy into the circuit. So he's showing what he's calling a link method. This is basically a loop. That's, you take a loop and you stick it close enough to the tuned circuit that some energy is exchanged from your square wave generator to the tuned circuit, and you see what comes out on the other side. If it's properly decoupled, you're not loading the circuit down. If it's heavily coupled, what it means is you're losing a lot of current through the probe and through the link, and that acts as a resistance, and the resistance is what drags down the signal rather quickly, so you don't get a proper Q measurement. The steps again are you loosely couple it, you put the 10-to-1 probe on one end, you trigger on a square wave. Don't worry about whether it's a square wave. You could have any kind of impulse coming up here. It's triggering on the leading edge, and the I'll say the signal on the screen, you'll see it'll have a leading and a trailing edge peak, which you won't see until I show it to you, which, let's see if I left anything out here. Okay, so the methods of coupling, you can do a number of different things for linking this thing. You can have, this is basically like an antenna coupling. You can have run a single loop through your coil, your inductor. You can try a capacitive connection. And I've tried all of these things. Basically, I haven't had any success with it, okay? And I'll explain why I think I'm not having success in a moment. So here's an example that I had. I was powering the circuit as you would with the square wave coming from my standard signal generator. And it's running at, I think the signal generator square wave was 4 kilohertz. It might have been 6. I can't remember. When you first look at the square wave with both signal, with both the left and the X and the Y. What I'm trying to say here, I've got two signals on the screen. I've got the input and the output. The input is the square wave, and the output is this almost flat looking messy piece of yellow. And right at the edges of the square wave, you can see a really steep spike going up and down. What you do is you focus in on that, you expand it out, make it as wide as you can. And that's what we're seeing below, okay? And this is how you take your measurement. So now I can just sort of say, okay, I can see it's this many millivolts to the top and the bottom, and it's half of that over here. So that's, say, I'm going to make a number up, that's 11. 11 times 4.5, that means my Q is about 50-ish, say. And this is what I was seeing. Now, if anyone has any questions, you're welcome to shout out. I can hear you, but I can't see you, by the way. Then the second thing is, oh, I shouldn't really do this here. Can you see that the channel 1 is very much smaller than channel 2? And that is because the coupling itself needs to be as slight as possible. And the effect of decoupling means your output signal is going to be much smaller in magnitude than your input signal. Now, I had trouble working with this, and the reason was, sorry, I'm going to the next page now, was as I decoupled it further and further, which is, let me just see if I can hide this thing so I can see what I'm doing. As I decoupled further and further in my series of different ways of coupling, I found that I rapidly ran out of available voltage on the output. Got so small that my oscilloscope couldn't trigger on it. Now, I did have a little bit of room left on my signal generator that I could have, like doubled it or something like that, and I could have carried on a little bit further, but I figured this is good enough for the purposes of this discussion. So first I started with a couple of capacitors. And what you're looking at is the circuit here. This is my grandiose test fixture. Let me see if I can remember. Okay, the signal is coming in on the red lead here. That's a signal generator. The red lead is not actually attached to anything. Oh, I'm sorry. The picture is different than let me think. The 10 picofarad capacitor was in place where this gimmick capacitor was. So let me just shut up for a second. I'll get to it in 3 more. Originally, this thing was just a little capacitor, okay? And then what I did is I started taking parts off of it. The 10 picofarad capacitor by itself, I got 7 cycles before it went on half, and the voltage peak to peak was great, 100 millivolts. So it looked okay. So that's a Q of 32. I tried it with a 2 picofarad. It got up to 41, and basically I was running out of capacitors that were that small in my bin, and I wasn't seeing much different. So this screen is halfway through it. I had a gimmick capacitor feeding it. Okay. Now the gimmick capacitor is just a twisted pair of wire. What I was doing with that gimmick capacitor is this is the starting point. I take a measurement. This is the, I think, initial measurement. Then I'd nibble a bit off of it, hook it up again, try it again. When you nibble a bit off of those twisted wires, you get less capacitance. I took it right down to about to a stub, and it still didn't make too much difference for me, but I was still having fun. And then finally, I think you can see just at the top of the picture is a loop of a coil. I put that in circuit and just sort of hung it close to the toroid, and I took it apart, moved it apart, tried it different ways. So essentially, each time I made these changes, I in fact advanced the Q a bit, but I was sort of peaking out at around 40, 50. And I had done one measurement, which I have a picture of, but I can't remember how I managed to pull it off, but I got up to 90. Now, why this makes this not perhaps the best way to measure it, I happen to know because I measured these things separately using one of the following techniques, is it's of the order of 220 if you have a good capacitor connected, and that was the good capacitor I think I'm using. So 220 Q is not 54. Now I would say that's not bad. If I had the ability to get a bigger square wave generator, or maybe I'm dealing with a problem with my 10-to-1 probe, because as we know, those things aren't actually a megabyte or, a meg ohm or 11 meg ohms at all. They're much smaller than that. This was at about 7 megahertz, by the way. Another way I might have gotten a better deal out of my test is to change the inductance and capacitance so I was measuring closer to the DC side, and the 10-to-1 probe would act more like a 10-to-1 probe, and I bet I would have got a higher number. But bottom line, this is just crazy cool that you can do this. If you have a better scope than I do, or if you have a better square wave generator than you, or you have other ideas that you want to reveal as to how I may have tried to cable these, energizing the circuit versus the reading the circuit, that's all cool. I mean, you can just play with this thing. So I thought this would be one of those fun Christmas projects if you have a little time on your plate to try out. All you need is a scope and a couple of components, and you're out to go. Okay, so what I was going to do next, since I'm doing so well for time, is I'm going to flip to the book of Mr. Hayward. Wes Hayward, in his experimental methods book, has a chapter of about a page and a half, a section of a chapter on page and a half, on various ways that you might attempt to measure the Q of a resonant circuit. I'm using these now because before I talk about a vector network analyzer type approach, I would point out that anything you can do in this section will work on anything like a spectrum analyzer, an SNA, if that's not considered to be a spectrum analyzer. It works on, it'll also work on a VNA. You need to have a frequency versus magnitude in decibels to pull this off. You can also actually do this with an oscilloscope, as I'll show in a moment. So first thing I'm going to tell you about this loaded versus unloaded Q and why it matters. I was talking to it just a moment ago, and I'm going to show here. I've got this circuit, an LT Spice simulator, and I have an inductor and a capacitor, and this resistor is a representation of the inherent Q, which is normally called unloaded Q, but it might also be called, what does they call it? Yeah, they call it QU. I use QU and I use QE for loaded for a reason, because there's also inductance, and I want to use the L for inductance. So here we go. I set this thing up so that if I were to change the two resistors on the input and the output and vary their values, that I would effectively load this circuit down. Currently, I chose to use 10K, which means that my Q is 100 at the frequency I set this at. Okay, so the unloaded Q is 100, but you don't actually see that when you place it in circuit. So what you can see is here, if I pretended that I have not so much a resistor, but a transformer that's transforming a 50 ohm input, and if taking it on the output up to 5K, I would see something that has almost no loss and kind of a wide curve. If I actually had a 50 ohm connected here, it would be straight flat. You would not see a line. It would be, at the scale I'm using, it would be horizontal at 0, and I thought it would be useless to have. But as you increase using the step parameter, I went up to 100K. As you increase the resistance that you're loading it with, that's decoupling the circuit. And it has the effect of increasing the insertion loss, which is what you were actually seeing in the ring down method. The insertion loss was the fact that I got a smaller magnitude on my output over as I increased the, as I decreased the coupling. But you get closer to the actual true Q of the unloaded circuit. As Hayward has pointed out in his book, is when you get below 30 dB, what you're doing is you're basically getting a Q that's pretty much identical to the actual unloaded Q, and the formula is showing on this chart here. This is the magic sauce that he uses a lot. You see this on the internet quite a lot, and I don't know if he derives it in EMRFD. I've got a book where he does, but basically, if you take the measured Q, which is Q effective, and you divide it by the unloaded Q, so put in this formula, you get an insertion loss, which means if you can measure an insertion loss and a Q, then you can actually determine what the unloaded Q was. So unlike the ring down method, this is a mechanism that will allow you to actually figure out what the Q was, even though you're getting effectively you're not actually seeing it on the screen, I guess. Okay, so here's how he does it. What he does is he replaces the resistor, the large value resistor, with a couple of very small value capacitors, so that you can terminate in your standard 50 ohm on the input and output. So you can plug this, your generator, and your output. You can use this as an oscilloscope measurement. You can use this as a spectrum analyzer measurement, and you can put this in a VNA, and they all basically produce the same result. What you got to do is you need to use very small value variable capacitors, trimmer capacitors, because depending on the frequency that you're measuring at, you're going to need to tune this thing down so that you get an insertion loss that's high enough that you can essentially ignore it for the measurement. So I had a couple of trimmer capacitors that were, I measured them, I measured like 1.5 to about 10. And I have to say, when you're measuring stuff that small, you can't tell if you're measuring noise in the air, but they worked in circuit, so that was fine. And then what you do is you measure the bandwidth, because if you, I'm sorry, I forgot to mention, this is a standard circuit for a bandpass filter, except for the weird capacitors there. That's a bandpass filter. So what you have is you have a peak where the inductive reactance and the capacitive reactance are equal. So you, at the resonant frequency, you measure the 3 dB points just like you do, and that's your Q. If you've got enough insertion loss, you're done. In fact, as I'll show you in a page or so, this is how you can actually correct for not having a full 30 dB if you can't get it by this technique. So here's my fancy ass test fixture that I made. I borrowed another. I was testing how if I could drill pads in ages ago, and I found this in my kit, so I used it. What you're looking at here, edge on, is a PCB board with an SMD capacitor on it. This is a capacitor that I bought to give me a known Q. So it was something that Hayward mentions in one of his sources, and I will be showing it later, I guess, in the presentation. What that is it has good charts that allow you to trust that you're getting a Q that's significantly higher than the inductor, such that you can actually use this as your basis for measurement. So it's as if it's not there; it's infinite for the measurement. So I did this actually with my spectrum analyzer. I did it with the Nano VNAF, and I did it with an oscilloscope. With the oscilloscope, what you have to do is you have to measure the voltage you're getting peak to peak from the signal generator. And if you want to get 31, I say if you want to get 30 dB down, I believe that works out to 1/30th the magnitude out of this thing when you put it back in circuit. So you make the voltage big enough so that you cut it in 30. Then you put it in circuit just as it's shown there. And what you do is you twiddle these guys until at the peak, the magnitude that you see on your oscilloscope is, well, 1/31st or something like that, 30 dB down. That's very simple. If you put this in the oscilloscope, in a signal generator, a spectrum analyzer or a VNA, you're doing much the same thing. You play with these two knobs here, the two capacitors, until you get the magnitude low enough that you can more or less take a direct reading from the Q. And I have some readings here. There are, for the purpose of the kind of measurement we're taking, these are basically the same. I know they're different numbers, but Q is not going to be a very precise measurement if you're trying this. And they didn't have identically the same frequency and identically the same bandwidth, and that has to do with how the circuit was tuned and what I had it in, what I was using to measure it. Okay. I like this because you don't have to have an accurate amplitude measurement. All you're measuring is bandwidth. That's a simple thing to measure. And as I can say here, you can measure it in multiple things. One other thing about Q again, this formula, I just did a little table here. If QE over QU, which means the actual measured versus the true value, engendered was at 0.99, you'd see a 40 dB loss. And if you go right down to 0.95, you get 26 dB loss. It's very forgiving. And if you actually know what kind of insertion loss and you can measure it, you're getting, well, you can correct it, right? Because what you would do is measure the Q and divide by whatever these numbers are that corresponds to the insertion loss you're seeing. So you can get an accurate value. Okay. Now it's time to talk about the fact that I'm dealing with resonators and there's Q and inductors and capacitors. I set this aside for a bit because for me, at least for the problems I'm solving, I'm actually going to be dealing with the resonators anyways. I'm not necessarily, I don't really care what the Q of the inductor is. I'll probably put it in circuit, I'll probably measure it in my test gear with the capacitor that I'm working with it. But there is a formula here that relates the Q of an inductor to the Q of a capacitor in a resonant circuit. So what you're measuring is L here is the inductor and C here is the capacitor. If you have any appreciable Q, if you have a small Q in a capacitor, it's going to act to lower the Q of the circuit, which is the way this works out. This is identically the same formulation of a parallel resistive circuit. So if you put two resistors in parallel, the overall resistance goes down. What people normally assume when they take these measurements is that Q is basically infinite. You need not pay attention to it. Now, as I was checking through my components and trying to do this measurement, and the reason that you saw me using a special purpose-bought capacitor for my measurements is I was finding that the Q of the capacitors is actually quite low. It's close enough to the inductor that the Q of the measured circuit was significantly lower than it ought to have been. That's because I buy shit. Sorry for my French. When I go Google and I use an eBay purchase and I buy some cheap Chinese stuff and I get what I deserve. Okay, but I did test mica capacitors and I had some NPO capacitors. NPO were supposed to be very high. I had some that were and some that weren't. So what this taught me is you want to be sure you want to measure, and hence there's some value in hearing how to do it. His special brand, he got some mica SMD capacitors, and I'm pretty sure I know why he bought them. It's because they published curves which are easy to interpret, and I don't think I have both sets of curves in my deck, but lots of capacitors are for sale now that you can buy off DigiKey that are very high Q, but it's very hard to interpret the data sheets down to HF, which is where I live, because they basically just go to they only may come down to like 100 megahertz or something like that. And you can't be quite confident that you know what they're doing. And all data sheets say typical values, by the way, not we promise it's this value kind of thing. All right, so here we go. One of the second methods of, both of them are attenuation-based methods. So I just used the parallel case for this example. What I mean by parallel, it's a series circuit going from the source to the detector with a parallel resonant circuit in it. There's another one which I call series, which is it's a series resonant circuit, but it's connected in parallel. What you would do is, if you can imagine taking out the capacitor and inductor and shorting that line, then you put the capacitor and inductor in series from here to here, and they have the same effect. If you have a series resonant circuit, it has a null at the resonance. If you have a parallel resonant circuit connected thus, it also produces a null. Because it's your parallel resonant circuit is usually connected between the signal and ground. All right, so look at that scary formula there. Straight out of his book. What you can do is you set your circuit up like so. It is connected to a 50 ohm source. You need to know essentially what your zero level is. So you have to zero it to know it's at, say, whatever it is for your device, like negative 20 dB. You put the test fixture in place and you measure at the resonance, at the frequency resonance, you look for the depth of the null, which is the attenuation. In this formula, it's A. You also have to know what the inductor is in the way he's written this formula. He's again making the assumption that C is perfect. He's using his magic capacitors here, and that's again what I had to do. And you plug that formula in, it'll compute a Q. So this one, I would say, isn't quite right for an oscilloscope measurement, but it certainly works in a vector network analyzer as well as a spectrum analyzer. So what else did I miss here? That's the inductance, the frequency, megahertz and microfarads. Z is going to be 50 for any measurement I think you were taking. It's actually the source and the detector resistances which are kept the same. Okay. So I did this and I measured the same thing using this text fixture, where you can see the SMD capacitor that I'm using and sort of more face on. So the capacitor and the inductor are wired in parallel and connected to the two SMD connectors. This one's a little harder to use a VNA for, and it's easy to explain. When you calibrate a VNA, you have a short as one of the steps you have to calibrate. Open, short, and several others who are slipping my mind right now. To get the short, you actually have to take this thing out of circuit and wire short across that. Then you have to take it back out. Whoops. And the problem with that is it takes time. And also, there's some risk that by doing that, taking it in and out, somehow when you put it back in circuit, the measurements you've already taken are not the same. Like your, I don't know, your open might need to be retaken. And so it's not ideal. There is another way to do this, I think, that I happen to like. But anyways, you got to put your parts in there anyways. So what did I find? In this particular one, by the way, if you look at the screen here, that says minus 45. The 0 in this was actually 20, so this wasn't actually showing a true value. I just snapped the picture before I dialed it in. On my spectrum analyzer, I suspect it's probably true of any spectrum analyzer. You have to dial the RBW, where is this? RBW, that's basically the bandwidth of the IF. Quite narrow, because if it's as wide as this is, it's collecting a lot of noise from the ambient environment, and it brings the floor up. So it went down to minus 45, and that was its bottom at this bandwidth. By bringing the bandwidth in, I get a true value. I find on my system, like 3 kilohertz is 3 kilohertz is pretty close. If I take it down to 1 kilohertz, it doesn't change anymore. Okay. And this is the actual what I measured. It was like 50.1. So I got 196 here. By the way, I think this is the same setup, okay, as the previous one. So that's similar to the previous result. And I got this largest value, which is large enough to question for the NOVNA, but I wouldn't trouble it too much. It probably was an error of a very small error of calibrating it. But I'm going to say again, that ain't a lot different than this when you're measuring Q. It's largish. It's not 5. If it's 500, it's big. But that's kind of what you got to get used to here. Plus or minus 20% is a pretty good measurement. All right, so well, I'm doing pretty good. I think I can make it pretty much to the end of this section here. So I'll carry it on for another 10. So I'm going to show you the one measurement that's bouncing around the internet of taking a measurement using just an inductor. Okay, so this is, I'm going to use some jargon here for people that don't know it. You do the S11 measurement, and you do that by taking your test fixture and plugging it into the generator of the VNA. And then when you're using the measurement, you're looking for an S11. I'm doing, I did a lot of work with Nano VNA Saver. Can't remember if there's anything about that in my deck, but basically what I found was an incorrect result. Down by a factor of 2, it was like 85 or so. And again, it's this toroid, which I happen to know is a couple of hundred. And I did some searching around. I can see some people making claims that they're seeing good values for capacitors, by the way. They may be getting it. They may not be getting it. They might be misinterpreting it. I'm inclined to say that if they read it, they read it. Problem is you can't be sure it's right. because I think one guy I saw said 165 for what I would read as about 250. So I'm pretty sure he took a reasonable sounding value. That's good. Okay. What you want to be able to do is have more than one measurement technique in your toolkit, which is why I'm taking you slow through this. Use more than one measurement technique to compare results is what I recommend always. Now I have two text fixtures that I'm using more often than not. I'm using the attenuation method and the bandwidth method, and I normally do a series of measurements using one, and I do a couple of cross checks with the other, and I find that keeps me sane. All right, so it didn't work because it was having trouble reading accurately the series resistance of that inductor by doing it this way. Now, there's a gentleman whom I have in PA3A has a method that he suggested you use, which I tried, worked, and it worked like gangbusters. Now, what he did was he used a shunt LC. This is actually the third one of Wes Hayward's methods. A shunt LC is, you can't really make it out, but the inductor is connected directly between these two, the input and the output SMAs. The SMAs are touching each other there at that landing. The inductor goes to the landing, picks up the capacitor, which goes to ground. So you're shunting the resonant circuit to ground. And one of the things you can do with that is you can use this circuit to measure the resistance using DNA Saver at the apex of that attenuation. So his suggestion was you get yourself an LC meter and you measure the LC. By the way, you can measure LC extremely accurately with an NLV. I know you guys probably know this, but that's not a problem. It's measuring the Q that gets difficult. This particular schema is not an S11. Sorry, that's not an S11 measurement. It's an S21 measurement. I apologize. So basically, you're going from the generator straight through to the receiver on your nano VNA. And then he says, because you know the inductance value, then you can measure the resistance, and then you can measure it. You can do a computation, and you get 220, which is what I expected to see. So it does work. But on the other hand, Wes Hayward's method is just measure this axis in decibels and use a formula. I will say that I didn't include the formula for this. It is different than this formula. It's in his book, and if there's interest, I'll find a way to get it to you guys. But when you're using the series parallel circuit, I think some of the elements of this computation are flipped on the over the denominator and stuff like that. But it's a similar kind of calculation. So this is basically when doing this measurement. You use a spreadsheet, I think. All right. So long story short, I'm dubious about being able to use the S11 method successfully all the time. I didn't have success with it. I can excuse that or explain it away as an error in my technique of, say, taking the calibration measurements. But I was doing a lot of calibration during this period, so I think I'm comfortable with the steps. I just don't know what I did wrong in this case. All right. So quick review. Ring down. I never got a good result from this thing, and I never felt bad about it. It was just a lot of fun to do this. I don't know why. Maybe that's not your cup of tea. The bandpass method, and I'll stop for a second and just mention, Hayward doesn't call them this. I'm using this name because I need to distinguish the darn things. Ring down is a commonly used name on the internet. Don't go searching for the bandpass method. You won't find it. You've got to look at Hayward's book. All right, so this is excellent. It does have repeatable results. It can be done with an oscilloscope, any kind of spectrum analyzer and NLVNA. I will say that from time to time, I have periodic problems where this thing doesn't seem to track right. It's kind of like I have to take it out of circuit or shake it or something crazy like that, because shaking it personally objectionable to me. Like that's not the way you treat your test equipment. I ended up not using this one the most, but I have to tell you it's very reliable, and it's a simple measurement to take. This is the one I was using. This isn't the one I was using for the Hayward's attenuation methods. Actually, use this one. This one will work just fine and is actually working according to the picture I showed you. I just didn't bother to compute it on the VNA. It's a little bit more difficult, I think, because for the spectrum analyzer, I had to, find the resonance, and I have to drill in to expand the lower the residual, the RBW, whatever that stands for, and narrow the bandwidth so that I got an accurate attenuation. You don't have to do that with the bandwidth method up here. Reason is that you're really dealing with the top of a curve. You're not dealing with the noise floor when you're doing this. It is 30 dB down, but that's not the noise floor. So at no point did I ever have a problem finding the peak and the Q using this technique. This one took a little bit more work, but I never had any problems with it giving a bad reading ever. Like I didn't have to shake it. Not shaking your test equipment, it's good, I think. And this will work just as well. Just another way to do it. This one is a non-starter for me. You're welcome to try it. And by the way, if you have tried it and you've had success or you want to try it, anyways, just go for it. Like, feel free. Again, the series shunt is you measure the darn thing as an inductor. The inductor measurement can be done in a nano VNA by sticking it in this circuit. The inductor would go from here to here in a circuit, and I think that that's the way it does, and it'll measure the inductance. I believe might be a shunt. I can't remember. Somebody will know. And that's it. I actually made it to the end. I will come back with some actual measurements taken. I want to give you a preview of what that means. Inductors measure as inductors, but if you're going to try measuring, you want to have a reliable, trusted capacitor. And my sense is don't trust anything unless you have a way of measuring it. I have, once I bought a boatload of variable capacitors in a crate at a ham flea market. I've looked at a number of the variable capacitors, which air variable capacitors, I should have said, and they are deemed by urban myth to have very high Q, and well, they don't. They have normal Q. They're not much better than run-of-the-mill ceramic capacitors, I'd say. And the reason I think that is they're old and they're dirty, and they're not going to get clean because the contacts themselves are probably the problem. And I think that were you considering attempting to build yourself an electronic Q meter, which I've left out of my presentation today, you would find trouble sourcing a capacitor that was of good enough quality to be used. And they do use variable capacitors in that particular instrument. Okay, so Eric Kleingeld is my guy I went to for the VNA. There's a whole bunch of things that Wes Hayward says about this. He was doing a kind of a big long trip on, I think he was making, he was doing a shortwave AM radio, so he was trying to measure the Q of a number of different resonators, and he kind of went down the same turkey trail that I did, so I happily followed him. And this is the guy that does the cool page on ring down method. Done then. I'm going to close. If anybody has any questions, let me know because I will embed it.
Okay. Ken, I saw you had your hand up earlier, so please go ahead.
Yeah, let's go back to the coupling thing. I ran into that same issue with the SA612 when we were trying to measure the frequency of the analog VFO, and no matter what we did, we couldn't get an accurate frequency count because the external caps or inductors or just the scope probe itself was loading down the circuit and changing the frequency.
Actually, that's true, and I apologize for not mentioning it. It does move the frequency.
Yeah.
It moves it a very, very, very small amount. It's certainly not enough in this particular measurement to move it enough that the actual magnitude of the Q you measure will differ by anything. I have reasons to say that from my experience measuring, but the Q varies relatively slowly. And the amount that I saw changing on this, give me a second, was of the order of about 100 kilohertz at 10 megahertz. So it's too small to change the magnitude of the Q that you're measuring. And I apologize for not mentioning that. I should have called that out. You don't get that unless you're using capacitors here. I don't know actually how this circuit is. I actually can't do the math to figure this thing out because I just can't. I do reckon the C's are part of the resonant circuit when you do this, but I don't know. The simplest way to explain it is it looks like a big resistor, but it works fine.
Yeah. Well, with what I was doing, I was trying to be able to figure a way of accurately reading the frequency of the VFO so that we could have a readout for the analog VFO. The problem was, no matter where I put my scope, or doesn't matter where I put my coupling capacitor, no matter how big or how small it was always changing the frequency. I even got to the point where I had loosely coupled an inductor beside it. It changed the frequency. And I also tried to add a couple of turns on top of the inductor, and it threw it right out.
Mm-hmm. Mm-hmm.
So that's one thing you got to look out for with coupling sources
Mm-hmm.
from that. Also, another thing I would like to point out too is you'll see a lot of builders, designers, whatever, they're trying to couple with an additional inductor, or they're how to explain this? If they're using an inductor, they're making the big mistake of using an inductor like the FT 3743, 5043. And the problem with those is it will lower it down quite a bit because the Q is so high on those inductors, it just doesn't work. And that's why you don't use it for in a tuned circuit at all. So there's another thing you have to look out for.
So you're saying the Q on the 43 material is high?
Very, very high. Very high.
Yeah, I didn't get a good measurement. I was doing a measurement of 43, but I thought what I was measuring was actually a low value. And when I looked up I looked up to see what the cause was. What I read is that it's acting as a resonant frequency. It acts as it's a good resonator below 1 megahertz, and above 1 megahertz, it starts becoming a really good transformer, which a wideband transformer doesn't necessarily need any Q. So I think I internalized this as the opposite of what you said for that material. 61 material works fine. I was using it to make toroids down in the low end of the HF range and top end of the BU frequency.
Okay.
So I did want to show you this favored thing of here it is. If you still can see my screen. This is the Cornell Dubilier MC series. You can get this off DigiKey. This is what was picked by Wes as his preferred choice And the reason is that unlike any other capacitor that you see specs for, his capacitors in this chart are basically flat and then they roll off. Okay, they do roll off, but most capacitors go sort of straight up when you see the curves, and you can't see, again, you can't see the HF region. So, you know, this gave me a mechanism by which I could take a capacitor, buy it, and say I'm trusting. It's close to what they say it is, but just following that curve along a little bit. Most of my measurements are along the center line here, where most things are about the same. So, if you feel like paying up, and these things are dumb, really expensive, you can like a 250 for the cheapest, I think, or maybe it was 350, and then they go up by the size. So the 470 was like $9. So I don't recommend that necessarily, but they're available to you. Many other makers will sell you capacitors, but you're basically going to be, if you're using a data sheet, guessing at what the magnitude of the Q of the capacitor is in circuit. Some of them you can probably say, and without holding your nose, that it's too high to imagine that being a problem, but I didn't want to go there. Good enough for Wes, so I took it.
Wayne, it's Michael. My first thought looking at that graph is my first thought was, well, if I do most of my stuff around 7 megahertz, and I thought, well, okay, if I do that, then maybe I can pretend that that curve is basically flat and they're all the same. But in fact, if you look at the Q on the left-hand side, there's big differences in the flat part of the sort of the under 10 megahertz part of the curve. So you really can't do that.
Okay, so let's have a look at this thing. The really biggest one was 1,000 picofarads, which I just don't really want to play with. So I'm dealing in this region here at 10 megahertz.
Mm-hmm.
See it?
Yeah.
So this is 1,000, 2,000, 3,000, 4,000. So it's between 3,000 and 4,000. Let's say 3,500. You happy with that? Then that's what I did. That's the way you,
Okay.
that's how Wes did it, and that's how I did it. And that's the kind of it's kind of scary when you're used to taking precise measurements, but that's what you really do. I will say the the other names, Johansson Technologies has capacitors, and they sort of go off screen at 100 megahertz, and they're about the same here. So I really don't know how high they are at HF. And they could be better. I did buy a couple, and I tested them alongside a circuit. So put a toroid with one of these capacitors, take the capacitor out, put one of the Johanssons in, and see if they're different. For the most part, they were same, and sometimes the Johansson equivalent seemed to come in a little bit lower, which suggested they weren't as good as this. But I suppose that they're probably still within the so-called typical values. They're just not. I don't think this is outside of the norm. If you search for information like this on the internet, they're not high enough that I would consider them to be normal, always so much higher than the Q of a toroid that I would trust them. Like I need to test that first. Now, what I did see is a lot of my cheap eBay purchases being 200 to 400. I had some NPOs that I bought from an eBay seller in Canada, and they were brand name. They came in at like the 400 and 800 range, maybe up to 1,000 on one of them. So they're not bad, and they would certainly usable in circuit. It's if the Q is actually material. Normally, you build circuits where you have Q in excess of what you actually use, so that it's not really a design consideration. You're just dialing it in with whatever you're putting in the circuit. Those sorts of computations actually work. I had an application of this in mind where I wanted to very precisely know the Q, and so that was what was driving me in this exercise.
Okay, thank you very much, Wayne. Anyone else have any questions for Wayne? Wayne, you were mentioning that you were going to be doing some actual measurements at some point. How long do you figure it would take for you to do that? Would you have something in time for the January mixer in a month?
Maybe a bit longer. I've actually done the measurements, Eric. I just have to figure out how to make them easy to interpret.
Right.
And of course, I anticipate having made some measurements. I'm going to say that one must be wrong because it doesn't fit this curve I'm trying to draw, and go back and remeasure. That's why I figure I'll take a little longer. I'll know once I start charting them. So let's say
A couple months, maybe.
a couple months for sure.
Yeah. Okay, that's great. Thank you very much for that very detailed presentation. So,
Well, that one wasn't too much. I'll get back on.
okay. I think you're still sharing your screen at the
Yeah,
moment.
I'm looking for it now. I hid the actual.
There we go. Yeah,
Okay.
I think we are good now. Yep, we're back to the grid. So, all right. So as there are no other presentations that were brought up at the beginning of the meeting, we'll start with our round the screen. What's on your workbench, or what have you been doing? Whether it's ham radio or otherwise technological related, just to see what's on your mind. So,
Eric, Eric,
yes, Michael.
Michael, could I ask a question? At the bottom of the screen,
Sure.
I get the little toolbar with the mute and the video and all that stuff,
Yep.
and the hang up thing. That was interfering with Wayne's presentation. Like some of the slides at the bottom of the slide, he had stuff, and this thing, I couldn't get rid of it. Is there a way to just get this thing out of here, or do you just have to sit and live with it?
I think if you just click on your bottom bar, like where all of your toolbar on Windows, that should make it auto hide. At least it does for me. So for the first half or so, I think Wayne had his sharing note up with, which that's not what was blocking your view. I think Wayne hid that partway through his presentation. I should have mentioned that earlier. First, I thought that was on my screen.
Sorry, I didn't realize it was visible on your screen.
Okay.
Yeah, I think it not until you got to some of the charts did it actually make much of a difference anyway, so not to worry. But yeah, I think that's all it is, Michael, just clicking on your toolbar at the bottom, and that seems to make it disappear. So I have to be careful because for the recording I can't even move my mouse over the screen, or else that toolbar reappears and that becomes part of the permanent recording. So all right.
Yeah, don't move your mouse.
Yeah,
Yeah.
That's what I find. Keep your hands off the mouse, and it'll go away by itself.
yeah. Or have a dual
Don't-
screen maybe, and keep your mouse on the pointer on the other screen if you're wanting to see the full screen. Definitely, I have to do that for the recording purposes here. But anyway, so far so good. The nice thing about this recording feature is they do seem to be working out some of the bugs, the Jitsi people. So we've had no problems making one continuous recording, even if it's longer than 100 minutes. I think we've exceeded that capacity, and the file sizes seem to be a little bit smaller, which is kind of nice too for the manipulation afterwards, editing and what have you. So. Okay, so actually first on my screen as it's displayed on the grid is Wayne, but we know what Wayne's been up to, so I think we can pass on that unless you had anything else. But if you're good, then Al, I have you next on my clock here.
Well, first off, Wayne, thank you very much. That was a little bit over my head, but very interesting, and I think I'm going to have to try one of those methods. It looks quite interesting. Apart from that, well, this is December, and work is keeping me busy. Not too much time to get into the shack. I think I mentioned last time I was trying to build a digital readout for my regenerative receiver. I got onto AliExpress and got myself a little $15 frequency counter, and I was actually able to make it work. I was just able to take my my receiver, and I don't know whether you can actually see in there. You can see the large red toroid there. Just a couple of pickup coils of some enameled wire, and I'm picking it right off of the oscillator, and it actually works First, I had to put in a bit of a buffer amp, so made a small little buffer amp with a J310 JFET. Is that in focus or not? I'm not sure. Anyhow, just a very basic circuit. So seems to work. So I'm just getting into the stages now of drying up a chassis for it. I'm going to mount it all up. So hopefully by the new year, I'll have it mounted on a aluminum box, and I'll have a digital readout for my regenerative receiver. Apart from that, nothing else to report. Life is good. Good to see everybody. So who's next, Eric?
Okay, thanks, Al. It sounds like you have been busy, even though you claim not to be. Your bench is active, so that's good. All right, we have lost one or two by the looks of it. Hopefully they'll come back. But Charlie, actually, I've got you next on my grid here. So anything you'd like to share with us?
Well, I've been working on some APRS equipment for doing some remote control and remote telemetry, and I've been working on a circuit board for use by another club, monitoring some remote repeaters. I've got a circuit board out at this particular point in time, getting manufactured. So when that comes back, I'm sure I'm going to go through a long period of putting components in and figuring out what I did wrong in terms of getting it laid out. In the interim, while I'm waiting for those boards to come back, I've spent today trying to write some Python code to run an SI 5351 chip to be able to just pass it a value. I don't know if you're familiar with it or not. It's a digital clock generator chip that's used in some high-speed computer systems, but it gives you it's very useful as a frequency generator. It has 3 independent clocks that can be in phase or not tied to each other. It's quite a powerful device, very complicated, and calculating from, passing it a frequency, calculating the values to load up its registers so that it generates the clock that you want is quite a challenge. I was working on it a few years ago and left it in frustration and went on to other things. And I thought this is a good time to revisit it while I'm waiting for those boards to come in. So that's what I've been up to.
Okay. All right. Thanks, Charlie. Good to have you with us, by the way. I did notice there was another fellow who's on here, Assad, I believe. It seems that he has dropped off the call, and Howard had to leave as well. But I'm not sure if Assad was part of the Kingston group or not as well. But maybe he will come back.
The name sounds familiar. I'm a fairly recent addition to the Kingston group. I just moved into the area in May timeframe. I've spent the last decade or so in the Yukon, working with the Yukon Amateur Radio Association up there. So.
Okay.
So I'm just getting to know the members in this area.
Yeah, very good. Okay, well, great to have you with us. All right, Hassan, what's going on, my friend?
All right, so last time I think I told you about my horizontal dipole. So I kind of mounted it a little bit higher, got it to clear the roof a bit, and I was playing around with that. I had to take it down because I think it got snagged on the roof tiles. So current project is I have to redo the T connector that connects both ends of the dipole to the ladder line. So I'm going to have to take it apart and do some proper strain relief on it and use a smaller piece, because I think the large piece of plastic I use is heavily, and with a lot of Kapton tape, is weighing it down quite a bit. It sags a whole lot. So that's part one. And part two is I think I have to make a proper hook, because it fell off the tip of the fiberglass pole, so I have to drill a hole through it and find a way to kind of connect it properly. But it's amazing. It really outperforms my vertical, and I'm amazed at the performance. And it works even at the into the VHF bands with my SDR. I can get a lot. I can actually decode kind of airplane traffic overhead really well with it. So that's the one. I also mounted it higher up on the tree. So yeah, horizontal dipoles are amazing. So
Hassan, how many ground radials do you have on your vertical?
on my vertical, I have 3 resonant radials.
Yeah. Okay.
So this thing, yeah, I think I have to add the 4th one, and then I'll probably have to add another set for the different bands. But I think I only chose 40-meter radials for the vertical. But yeah, that's a good point. I should extend that as well this season.
Yeah. What I actually learned with my vertical is the radials, resonance not so important apparently. That's why I gather the consensus is, just make them long, make them as long as your longest band, and they couple to the ground basically. Once they're on the ground, the resonance is not as much of an issue. So, but yeah, the more the merrier. So I'm in progress to put about 40 of them down, something like that. So.
Okay. Yeah, so the thing is, I don't have enough space to actually put in the ground. So these are on the fence and they're elevated. So what they tell me is elevated radials have to be resonant.
Right.
But radials in the ground can be short, and higher number is better than longer length. So for a given length of wire, like 10, even if they're like 8 feet long, but like 100 of them, that's better than having longer ones with fewer number.
Right. Now the only question is, what does the XYL say about the elevated radials? So.
Well, the dog next door was barking when I was putting them in the fence. So, but they're between the fence posts, like between the fence boards, so you can barely see them.
Yeah. All right. Very good. Stealth. I like it.
Yeah, that's all.
Okay. Thanks, Hassan. All right. I think I'm going to continue around the clock here. So, Kevin, you're next on my list. What's moving and shaking with you?
Well, I'm finally at a point where I can start building again. I'm getting my bench all set up and stuff, or at least something set up that I can work efficiently or more efficiently. So I've got that SigGen attenuator mod that Peter and I worked on before COVID, I think. So I wanted to kind of finish that. So I'm going to work on that. And then I got to throw an end fed up in the backyard so I can actually use my radios again, of course, now it's winter. So now is the appropriate time to do antenna work, right? So you do it once, you get it right, and you don't mess around. So I want to do that. And actually I have one of these Arduino PLC things that I bought again before COVID, thinking, oh, okay, well then I thought, I have lots of time during COVID. And of course I never did it. So I want to build that because it's like an Arduino board, but it's got like not industrial strength, but more robust IO, right? They're isolated and stuff like that. And I want to just mess around with that. So that's a kit that's been sitting in the bag for a while and it needs some attention. So other than that, that's what's going to be on the bench in the very near future. So
okay, very good.
Good intentions at the moment.
All right. Well, I have a little bit of a segue there into Arduino. So a makerspace that I belong to up in Richmond Hill at the David Dunlap Observatory YLab, they actually had an Arduino boot camp that I attended. I missed day 1. Unfortunately, it wasn't available for that. But day 2 was last night. So it was quite good, actually. I know very little about Arduino, but it was good. Basic programming concepts. It actually created a simple oscilloscope using the PWM pins, the IO pins, and so visualized it with a little built-in scope in the IDE. Converted to voltage, created a 3-channel with the various PWM pins, and then last night was that was kind of like day 1 that that I missed that I kind of did on my own. And then day 2 last night was I don't know, talking about a lot of basic electronics, but pull up and pull down resistors, and some basic concepts, but how it all ties into the Arduino. So I'm happy to report that it was a success, and so I'm a little more familiar with the Arduino. And actually, the course material I have is open to the public. So if anyone's interested in Arduino stuff and is not too familiar with it, you just go to ylab.ca, I think it is, and they will, all the stuff is there for you to get the concept down. So there you go. Anyway, all right. Thanks again, Kevin. Frank, I see you're next on my list there. You're muted still. So there you go.
There.
Oh, you're muted again, Frank.
Thing.
You're fighting with your computer.
Okay.
There you go.
I am. Anyway, last month we left partway through the QRP15 rig that I was working on, and I think we left it hanging on the Christmas tree. But I did get it working, and I put it back in the case, and in putting it into the case, something shorted out, and something new this time. So I put it up on the shelf. And I got kind of interested in something entirely different. Going back to the basics and everything, I'm building another direct conversion receiver. Only this one is using a permeability tuned oscillator. And in that situation, instead of tuning with the variable capacitor, which was mentioned, are getting scarce, and the ones that are hanging around are getting old, not too reliable, you vary the inductance. And the LC circuit then can tune. This one is built for 40 meters, and I have it so the PTO, as we call it, can tune from 7 to 7.3. The interesting thing, and it was promoted originally by Farhan, to use permeability type tuning in a transceiver he built and presented at, I guess, at Dayton last year, or early this year. And then it was picked up by a couple of people in the States, and they are using glue sticks for their inductor. So I went to the dollar store and bought a couple of glue sticks and see what I could do. And I'll show you the results let me see now. There we are. The glue stick direct conversion receiver. It's not soldered in the case at all. But the inductors, as they're used in Farhan's, uses a screw that goes in and out. But this one, it's a big knob rig as opposed to your current computerized equipment. And as you turn the knob, instead, I've taken the glue out of it, of course, and replaced it with a toroid. And as you turn the knob, the toroid passes by the coil, which is there, and produces the oscillation from 7 to 7.3. The rest of the circuit down at the bottom is the antenna. I can use the mouse here. Yeah, antenna coming in through a bandpass filter. That's all working, and it's going into a mixer. Now I'm using, in this case, 2 FETs rather than the normal 4 diode combination of mixer for this. And the space here and here will be used for the audio amplifier and that. So that's as far as I've gotten on the rig, and it's kind of fun to get back to basics, and very basic when you start playing around with a glue stick PTO. So that's what's on the bench now.
Okay, all right, very inventive.
Imagine taking the glue out.
Yeah, good point. All right,
What was that? I missed that.
Oh, Michael mentioned just make sure you take the glue out before you use the glue stick.
Right. Yes. Yeah. The glue comes out kind of easy, and you wash it out. But the only thing is don't dump it into the trash, because you're going to be dumpster diving for the little piece, the plastic piece, which is a key to the whole job, that you do need that plastic piece to glue or fit. Mine was a press fit, and I used a 68 toroid in there, and it just was a nice press fit. But you do need that plastic piece, because that's what the worm gear is on.
Okay. All right, Frank, thanks very much. Before I move on to the next on my screen here, I'm going to throw up a poll just regarding dates. Pick a date for the visit to the Hammond Museum of Radio, just what preferred date. We had settled a while ago on January as being a good time to go after the holidays. So I've put that poll up there. So if everybody can answer that in the meantime, and hopefully by the end of the meeting we can come to a consensus on that. That'd be great. Okay, so Michael, you are next on my screen. What's going on with you?
Well, I've been I've done a few unham related things. We have about 2,500 to 35 millimeter slides, and I've been going through digitizing those, which takes a long time. I've got a Nikon scanner here. I've just been doing that for days and days and days now, almost done. The other thing I've been taking time with is we converted our phones to voice over IP from Bell, and that just happened yesterday, and finally it's fine. But the tech savvy people told me expect phone calls from Bell and don't answer them. Well, I had about 3 calls every day almost for a week and a half, until finally they stopped calling. So I didn't answer the phone. Amateur radio wise, I've been working on the presentation for the I can't think now, the oscillator, the Colpitts oscillator, and that's coming. It's almost done. But so I was going to ask, Peter was talking about not having a meeting on December 20th, 22nd. Is that still the case? Are we still going ahead on the 22nd? Anybody know?
Yeah, Wednesday the 21st. Yeah.
It isn't, yeah.
I believe there were 6 that were willing to go ahead with the meeting. So we could have another poll, I guess. But, I think 6 is probably a quorum. So I don't think...
I'll be ready. Yeah, okay.
I mean, it is close to Christmas, and I don't think a lot of things are being kind of put on hold in that week before. Christmas is the Sunday, I believe. So, but, if you got an hour or two on the Wednesday night prior to it, then we'll go ahead. Unless anyone's scrambling to pick up last-minute gifts.
Where's the poll, Eric?
Sorry, where's the poll?
Where do I find that?
Should be
on the screen.
Yeah, open the chat window. I'm not sure what it looks
Oh,
like
okay.
on your end, if it
Okay.
prompts you for a poll, but I guess not.
Oh, I see it. Okay, fine. That's good. Thanks.
Yeah.
Okay. Nothing really else to report. I've been playing around with that and learning quite a bit, and having some issues with LT Spice, which I'll talk about at the meeting. And anyway, yeah. So that's about it.
Okay. Thanks, Michael. Dwayne, how you doing? Oh, sorry. I see, Kevin, you put your hand up. Was that regarding something that was mentioned?
Yeah, just for the poll, do you know, was there a specific time of day you were thinking about? Like, is this during the day or is this
Yeah, it'd be a
late afternoon or what?
it'd be
I
a
don't know.
daytime visit. I don't think the she said, again, about maybe an hour for a conducted tour, and then you can just wander about as long as you want. So it would probably be, like an afternoon. It's weekdays only, as somebody mentioned previously. But
Oh, okay. All right. Okay.
yeah, so I would think afternoon would be right. Maybe aim for early afternoon, 1 o'clock or something like that, and spend as long as you want.
All right. No, I just wasn't sure. Yeah. Okay. So that
Yeah.
makes a difference to me. Okay.
Okay.
Thank you.
Yep. All right. So hopefully that works for most. Okay, Dwayne, what's up down south? You're muted still, Dwayne.
Okay, so hitting it twice. Yeah, most of the home brewing I've been doing lately has been of the liquid kind of like the stuff that Peter does, getting some stuff ready for the holidays and stuff like that. Yeah. I didn't bother bringing anything out tonight. As far as electronics, I had a couple of little projects been working on. I've been doing like Pete and Bill and everybody and stuff been doing is the small modular things like that, and trying to get those things like that and built has been a little bit of a pain. So I printed up 3D printed a little PCB vise holder, a holder that works real well for holding real small PCBs and much easier to work with than trying to stick them in one of my larger ones that I use for full size boards and stuff like that. Other than that, hasn't been doing too much at all. That's it.
Was that a board you CNC'd yourself by the looks of it?
Actually, it's an etch board. I use toner transfer etching and stuff like that. But this is laid out as a Chuck Adams, what K7QO used to call it the Muppet style. The boards are basically laid out surface mount, and you just solder them to there, and they work out real well, and they're real easy to go and make, especially a smaller board like that. The Muppet method works real well with toner transfer, works real well. You don't have problems with losing the toner resist like you do with larger layouts and boards.
Okay, good for small scale projects. Yeah. Okay. All right. Thanks very much, Dwayne. Speaking of homebrew, on that front, unfortunately, Peter's not here to share this with, but I'm now the proud owner of a 1 gallon keg, so I don't have to bottle anymore, which is kind of nice. That saves one step. Pour right out of the keg. You only get about 8 pints out of it, but what the hell, right? So moving into the big leagues, but slowly. So. Ken, you are the last, I believe, on my list here. So.
Okay, not much really happening. Back in on the one weekend at Eric's farm, I picked up a QCX, an older version of QCX from Al Wolfrey. I ordered a optional AGC. I put that in. And now I'm just going through it, learning all the menus and everything and the testing of the circuit. I've got that going on. I've also ordered a couple of bandpass filters from Hans at QRP Labs. I want to see how we can integrate that into the DCR. make it much more simpler and less expensive. So I'm looking at that right now, and I'm also looking at maybe building my own 500 amp hour lithium iron phosphate battery. Um, very high charge, very dangerous if you short it out. But yeah, I'm going through the steps, and I didn't know that you can actually buy kits to put these things together. Um, 3 buys. You buy the kit, you buy the batteries, you buy the BMS, and you're ready to go. And I'm looking at a high output uh, battery to use for camping and going off grid or wherever out in the bush, and it'll last a long time. I've also been noticing these. One subscriber I listen to on YouTube. Um, he gets sponsored a lot about solar panels, and he's big time into these flexible ones. And he's got one that's probably a third of the size of your typical fabric solar panel, but the price tag on it's like $1,200. But I'd like to look into that as well. I'm planning probably maybe 5-6 years is we're going to go off grid, sell the old homestead and head up into the bush and build our own place and live off solar panels and well water. So that I've been doing a lot of reading and studying into that, and that's what's been going on.
I just put a link, Ken, in the chat window for a not too old, earlier this year, Ham Radio Workbench show that was all about battery builds, BMSs, and all that. So you might want to have a listen to that. It's a Canadian that was the guest of the show. So Dan St. Pierre, VE6. So anyway, have a listen.
Yeah, I'll take a look.
Yeah, that's a frequent topic on that podcast about battery systems, homebrew battery systems. So
yeah,
I'm not sure if they roll their own BMSs or not, or just off the shelf, but yeah. So, oh, by the way, Ken, I just received a few days ago your QRP Me bag of goodies here. So I do have it, there it is, just so you know, in case, whatever, I know it's not going to be focused, but that's it. So,
yeah, no rush.
So next time I'm coming through Brampton, perhaps, or what have you. Actually, I might be coming down Friday, so I could even maybe drop it off then. So
I won't be around on Friday.
No? Okay. All right. Well,
we'll make arrangements down the road.
Yep. Okay. Fair enough. All right. I think that is getting kind of towards the end. Myself, not much on the bench other than, like I said, playing around with the Arduino and the programming aspects of it. I now have access to a laser cutter, which is kind of nice. That's something that I had a 2-day, two evening seminar on, getting up to speed on safety and design, 2D design with QCAD, which is a freeware, I guess, or I don't know, trialware, maybe you'd call it, program for 2D design. So learning that. But anyway, yeah, so laser cutting and engraving is something that's in my toolkit now. So hopefully that might come in handy for some projects down the line. So that's about it. Otherwise, the rest of life keeps getting in the way. Happy to report that the vertical that we put up back in August, when everybody was up at my place, is still up. We've had some serious wind storms here, 90 kilometer an hour wind storms. I do take it down, put it horizontal when that comes, but I do have a guy wire on it the rest of the time when it is up. So happy to report that it's the stock model is still up and working just fine for the for the moment. There's some reinforcing things. I want to put some more guidelines eventually, but otherwise we're good. So. All right. So unless anyone has anything else to discuss, I think we'll call it a night. So next meeting will be 21st of December. You're okay to host that, Ken?
No, I'm not going to be around. I've
Not-
already sent a message to Peter.
To Peter. Oh, okay. All right. I wasn't sure. I
Yeah,
can't remember his message, whether he said that or not.
yeah. I got to take off on the 17th.
Yeah. Okay. All right. So that's a to be determined then, I guess, hosting. And but it looks like there's enough people that are interested. As far as the museum visit, we've got the majority looking at Wednesday, January the 18th, as everyone can see. Yeah, you can change your vote quickly, I guess, before we close here if you want. But I see there's an option to do that. But anyway, so I think we'll target the 18th of January. Hopefully, most, if not all of you can make it or make arrangements to make it. I think that would be interesting. It is in Guelph, so we'll make it there. No buses to be arranged, so carpooling, I guess, is going to be the way. And I think that is about it. If for whatever reason 21st of December doesn't happen for our regular meeting, then it'll be the mixer on the 4th of January in the new year. So. And yeah, I guess that's about it. So with that, thank you very much for your participation tonight, and we will see you in 2 weeks, and if not, in January. Okay, so keep safe and keep burning your fingertips. All right, thanks everybody. 7:30.
Night all. Thank you.
Good night.
Good night, everybody.
Thanks a lot. 73 to all.